Good afternoon, everyone. Today we're going to continue our discussion on machine learning using for regression. Let's have a brief review of the file that we were using. Okay, so we loaded the packages, these packages. These are what we're going to use. The very powerful Caret package has been we have been using for the past few sessions. And then there are other packages here that deal with the algorithm itself, machine learning algorithm like RPART for decision tree, random forest, XGBoost, and net for ANN, artificial neural network. Okay, I'll be adding some more later on for the shop, but we won't get that far. Okay. All right. So what we did was to download, identify the start date and the end date, and we downloaded the US dollar PHP, where the ticker symbol is this one. USD PHP is equal to X. Then we also downloaded VIX, the volatility index, and also Brent. And we checked if how many missing values there were, because it's very important to clean your data before doing any functionality or any program in machine learning. Okay, and then we found out that VIX has 92 missing values. USD PHP has, I think, 2 or 3, and then Brent either 2 or 3. Okay, and then we said that if we were only modeling VIX, then we could have used the NA.LCF, because that's a logical process to fill in or impute on the missing values the previous value class. It has a solid theoretical foundation. But we're not using only a univariate time series. We're using multivariate, which we're going to merge. So we'd like to see the effect of doing first an inner join. An inner join merges all your data, then removes those that are not present in any of your data. And with this class, by doing inner join, in particular merge prices. So I'd like to kindly check, class, if you have merged prices, because we're going to use that. Merge prices here. It's an XTS object, and it lists. I have it. It lists open, high, low, close, volume, adjusted VIX, and Brent. So could I have a thumbs up, or could I have a chat from you, class, just to make sure you have merged prices? Okay, kindly chat, please. Okay, thank you. Okay, for some of you, you already have the merge prices class, because we already did that. Okay, thank you. Then let's proceed, class. We have only the raw prices. We have to get the returns, because that's what we're going to model, the log returns. So we made use of, by the way, class, by the way, we were able to show that using inner join for all the original data, as compared to doing LOCF first and then merging, is the preferred method. Why? Because the retained number of observations were practically the same. And we said using LOCF introduces pseudo or fake values. Okay, so it would be better to just make use of the original data set, inner join, for us to arrive at the object, which we call merge prices. So that's what we're going to use here. So what we did was to compute now for the returns, because we have only the raw prices. So we computed for the USD PHP return, log returns class, type is equal to log using quant mode's daily return. We use the merge prices object, right? Okay, doing the same for VIX, Brent, and creating a next day target, which is our target is our dependent variable. Okay, so out of this class, we combine, okay, we merged the returns together with the target. And then, as I said, class, as we discussed before, when you create daily returns out of the quant mode, there will be introduced a missing value, an NA value, because the first observation, the first row, the first date, the earliest date, will have no prior value for with which to compute the returns on. So that will become, sometimes it reflects 0, sometimes NA. So we remove that to make sure that there are no NAs. So that's why our merged, our merged prices had 2214 observations, but when we when we now created our XTS object, there were 2213 observations. Okay, why? Because there we removed the NA value. Then also we this is an XTS object. We need a data frame, so we created the data frame out of the final underscore XTS object by getting the index from this XTS object. We know that index will allow us to get the dates, and then core data will be the actual data. Okay, so you now have final TBL. Okay, could we check class? Final TBL. You have the date, USD, PHP, RET, VIX, Brent, and then your target. Okay, so I hope you have that class. And then we went to features engineering where we said that we're going to create an object which contains the uh, features or the independent variables with which we will explain or model our dependent variable, which is our USD PHP uh, with the log k is equal to -1, and we named it as our target. So last time we had we there are logical and research-based justification for using the lag value, for using SMA short and SMA long. I just didn't provide here the journals or the articles. RSI, volatility, moving average, convergence, divergence, and then we have the Bollinger Bands, ADX, and two exogenous variables, which are VIX and Brent. Okay, so when we created class this object data for fits or features, this is coming from your final table, and then we appended here all the indicators, the lag 1, 2, 3, okay, the SMA short, SMA long, also the RSI, okay, the MACD, moving average, convergence, divergence, the what else here, Bollinger Bands, okay, and also the ADX. Okay, so these are the indicators that we wanted to use in order to predict our target variable, rolling volatility, and then we have our extraneous variables. So what we did was to create we merged all of this class, we joined it into our data for fits, and then remove the missing values. Okay, so and then so if we check class data for fits, okay, data for fits, kindly check that class. I hope you have it. Data for fits here, 2180 observations. So initially we had 2213 observations for data fits because it's the same as final underscore table TBL. But when we deleted the missing values, because when we incorporated the other indicators like RSI, etc., NAs were introduced, and then when we removed it, what happened was 2180 observations. So this is now our final data for feature update, etc. Okay. Okay, 2180 observations. So what next did we do, class? We created another object called final features, which were subsetting data for fits, and then just include the key features. What are the key features, class? It includes all your indicators, all your predictors, and then the last one will be your target. Okay, so these are your key features, and then your target. Okay, so we now have these final features. Could you kindly check? And please chat in the chat box if you have the final features object. Also 2180 observations and 14 variables. So final features, okay. It contains only your features, log ret, log 1, log 2, log 3, SMA, RSI, etc. These are our exogenous variables, Bix and Brent, and then our dependent variable target. Okay, and then 2180 observations. Kindly, please, in the chat box, please kindly confirm if you have it. Okay, thank you. Waiting for the others, class. Good. Okay, all right. We need to know first, class, because if you don't have that, then you can proceed because we'll be needing this object. Okay, thank you. All right, so moving on, class. So we said that we will have to, okay, we cannot use the final features object and create a model out of that because that will lead to, okay, so this is our data, 2180 observations. We said that we're going to split our data into train and testing. We cannot use this class because that will lead to overfitting, as you're creating a model which has been tuned to specifically that one, and then when you use it for to model new data, that might not work well. So the data available that we have, we split it into train and test. And then since we can use several ratios, we can use 80-20. Okay, 20% of 2180, that's 400. That's good enough data for our test data. Okay, so we're using 80 for training and 20 for testing. But however, we said that there's a difference between splitting your data into training and testing when you have cross-sectional data. Let's say like for classification class, for machine learning for classification. It's okay to use a random sampling. It's okay to use the sample function or create data partition using caret. Okay, because that will generate random 80% and 20%. Okay, but for time series, you cannot do that because you have a logical flow, logical arrangement of your data. So what do? Here, okay, we generated this object n rows, which is just the number of rows of the final features, and we know this is 20. This is 2180. Okay, 2180. And then what we do here is use floor class. Floor means you start from the beginning. Okay, and then consecutively we're using 80%. 80% of n rows, 80% of 2180, that will give us 1744. So we're going to set aside 1744 for our training data set and the rest for our testing data set. And we're not doing this randomly. We will have to arrange it in such a way that when we create our trained data, it will be from the final features 1 up to 1744. Okay, so that's specifically ordered from observation number 1, 2, 3 until 1744. And for our test data, it will be, okay, from this final object, final features, okay, then it will be n trained plus 1. So 1744 plus 1, it will be the 1745th observation, and then up to 2180. So this now splits our data into train and test and it's split logically. Okay, it's arranged according to uh, appearance class, so chronological. So if we run this and then just print, okay, training is 1744 rows, 80%. Testing is 436 rows at 20%. Okay, this just makes sure class that the number of rows for data for fits and is equal to the n rows. Why is it equal to n rows class? Because this final features class came from, okay, n rows is the number of rows of final features, and final features is exactly the same as as your data for fits. Okay, so it tells us that if they're not equal, then give a message that proceed carefully. Okay, so here it will not send any message because the rows are the same. So it will only send a warning message if they're not the same class. So anyway, uh, okay, so we already did this class. So generate your, no, sorry. This one, we'd like to see the dates class. We discussed this last time. So very quickly, this will generate class where we're using data forfeits because data forfeits has a date, while what's that? What's the name? Final features does not have a date class. So we can make use of data forfeits and then date, then print from 1 up to 1744, and then from 1745 up to 2180. So this one. So when we run this class, it will be 16486 to 19363. Where did this come from, class? I thought it will be the date. In R and in Excel, dates are represented by numbers. So the default in R is that number 1, okay? When you say number 1 class, that refers to 1970 0101. If it's negative, then it's a date before 1970 0101. So if it's negative 100, it means the day 100 days before 1970 0101. If it's plus 500, it means 500 days after 1970 0101. So here, 16486 means 16486 days after 1970 0101. Same thing true with the others. Okay, and then we converted this class, we converted this number into a date class, and then we also asked for the weekdays. So we ran this already last time. If I just a quick review class. So here we saw that 16486 is this is February 20, 2015, and it's a Friday. Okay, so just to check, our train data ends up to 2023-01-06. Our test data begins at 2023-01-09. So it's okay, it's correct. There's no overlapping. And then why is there a gap here? Because this is a Friday, as can be shown here. And this should be a Monday, as can be shown here, Monday. Okay, so just double checking our data. All right, so we now go class 2. Okay, we also said that we need to create a matrix because we're going to use this later. A matrix where we have only your features or independent variables. For our training data set, we call it XTrain. And then here we said ask that matrix. We're using our trained data. And then include all the rows. And for the columns, which names trained data is equal to target negative. It means do not include the target. So all the other variables will be included in our XTrain except for the target variable. Okay, and then for your Y train, we only need the target. Okay, XTrain for the independent variables, Y train for the dependent variables. Same thing with X test and Y test. Okay, this is our training data. This is our testing data. Once we have generated a model out of the train, we run it, we use it to predict test data and see if our model worked good or well, even with the data that it has not yet seen. Okay, that's our test data. Okay, so the first model class will be linear regression model. This is just the generic uh, um, model class we're going to use. The target variable or dependent variable will be a function of your different predictors, log ret, log 1, 2, 3, SMA short, etc., up to the exogenous variable VIX current and Brent current. All right. Now, we discussed this last time, plus the K is equal to 5. So let me just invite you once again, very quick review of what we discussed last time. Cross-validation is one of the most important aspect of machine learning using caret. Okay, very important to class yung cross-validation. So just by way of review class, this type of cross-validation is only good for non-time series. Okay, if it's a time series problem, then this will not work class. So how does this work? So take note that we have our data, 2180 observations, right? This is our final features. And then we split this into two. 80% for our train, which turns out to be how many? 1744. And for our testing data set, which is 400 plus something. I forgot. No? But the total should be 2180. Okay. Now remember, class, so this will be our training data. What we're going to do is develop a model using the trained data set. And once we have developed the final model, we use that final model now to compute to test to run the test model. So of course, this will also generate its metrics like Ramsey, root mean square error, mean absolute error, R squared, etc. Okay. So for cross-sectional data for non-time series, this is okay. Now take note that for cross-validation class, okay, you'll have to identify cross-validation. You have to identify how many folds, okay, how many folds or how many splits. Here, we're using 5 folds, which is usually the case, or it can be 10 folds class. If it's 10 folds, then you'll have 10 splits. So how is this done? Notice that we're only working on the trained data set. For cross-validation class, the test data set does not enter the picture. Okay, cross-validation allows us to split our data, okay, our trained data, split it into another set of train and test. Okay, so it's called your in-house sampling. This is your quote-unquote in-house data. And then we're going to split it again and create an in-house sampling. So how does that go, class? Okay, so if it's K is equal to 5, which means, class, you develop 5 folds. So let's take a look at this one, class. This one. So this is fold 1, fold 2, fold 3, fold 4, fold 5. It may be it may be equal folding, or it could be random. Okay. What's important is that we develop these 5 folds, and then one of them will be used for testing, and the others will be used for training. Okay. So what do I mean by that? We're going to create the model using this, and then after we create the model, we now run the model and perform it on the test data set. So when you do that, whether it's random forest or LM or XGBoost, you'll now be able to create metrics. For example, the metric that we're using is Ramsey, RMSE, root mean square error. Okay, so this split one will have its own Ramsey. The Ramsey is the root mean square error generated when we use the model we developed from the train on the test data set. Okay, on the test data set. And then we go to another split class. This time we'll use another batch of our fold here, fold 2. The others now will be your train data set. So what happens is that each of your data class has it's used also as a testing data, as part of your test data. Nobody, no data can escape becoming a test data. Okay, and of course, every data will be will become a a trained data set. In fact, if it's k, if it's fivefold, k is equal to fivefold cross validation, it will be used as a train 4 times, no? 4 times, and it will be used as a test data 1 time. All right. So we have here split one. You're able to compute your Ramsey. And then again, you have your split number two. So for split number two, you use a different set of training. Okay, so we have this 4, and then this one will be your testing class. Okay, and then you first create the model. You have now different data, and then you use this testing. Okay, you're able to generate now a model class for split number two, and then use the test data set, and then generate your Ramsey. Okay, so what will happen, class, is okay, what's happening to my mouse? Oh no, wait. Sorry about that. My mouse is oh no, wala. Asan na yung ano? Okay, wait. Sorry. Here, I provided the site. Yeah. Okay, so you'll have 5 Ramses class, no? 5 Ramses. And then you get the average of those Ramses class. You'll get the average performance of the Ramses. You'll also get the standard deviation of these 5 Ramses. You're able to develop the average Ramsey and then also the standard deviation of all the Ramses. You don't average the standard deviation, by the way, class. You have the 5 values of the Ramses, you get the standard deviation. And then with that class, R will generate a model, okay? It will tune the model and then come up with the final model. And then, okay, in coming up with the final model class, what does it do? It uses this trained data set, the whole of the trained data set class. The whole trained data set class. In order now to create your final model, which will now be used for your testing data set, the original test data set class. So all in all, class, you actually developed 1, 2, 3, 4, 5 Ramses plus 1. So for a 5-fold cross-validation, you're actually generating 5 Ramses, where the last Ramsey is now the final one because it's based on the overall test. Okay, but the other Ramses here are helpful in coming up with the final model. Okay, now for time series analysis, this cannot be class because, okay, suppose these are time series. Okay, so what will happen here? If you take a look at this, the first one class. So let's say the first 300 observations. Okay, so what are we doing here? We're creating a model here. This one, this data is to be our model class. And then we're going to predict this one, our test data set. That doesn't make sense, class. That's logically flawed. Because why? Let's say you have a data here happening to my mouse. let's say you have data here. Let's say December 10, 2024, for example. So you're using data December 10, 2024, and the others class in order to predict, let's say, January 5, okay, 2020, what's our date? Whatever, let's say 2020, for example. Let's suppose this is 2024. Okay, so it doesn't make sense, class, to use your future value in order to predict your past. No? This is not ARIMA class. This is not sort of an ARIMA model. Okay? What's happening to my mouse? Nawawala yung mouse ko. Okay, so how will cross-validation work with time series data? Okay. First, you should be able to split your data, class. If you take a look at your data here, so we have here the trained data set, and then you have your test data set here, class. So you notice you don't use everything. You first use this, and this trained data set is a value or values that comes ahead before your test. Okay, so the dates here, class, are later than your trained data set. So it's not the reverse. We're not using this one as our trained data. We're creating models so that we'll predict the if this is your test data. No. So what happens, class, is that we have what we call a rolling window. Okay, rolling window. So this one will be from a specific date to a specific date, and this will be in relation to this future dates, etc. So you keep on increasing your train and you keep on moving your test data set. Again, include this. Once this is done as a test data set, you can include that as part of the train, and then move on to the next test data, etc., until you're able to complete everything. Okay, so that's your rolling window. So let's take a look at how it's done in R. Okay, so it's called your walk forward validation or rolling origin evaluation. So I did here some notes. Okay, class, please take time to read this. They're just short. So this is what I was telling you, look ahead bias. Okay, you're using the quote unquote future data in order to predict the past. Okay, so that doesn't make sense, class. That will tend to a bias which we call look ahead bias. All right. So there are some metrics that we need to compute, class. So this is now the initial window, class. The initial window is the number of observations that we'll use for the first training. Okay, so that will be our first training. That's our initial window. For example, this one. Let's suppose it's let's say 400 observations. Okay, this one can be computed with this one, class. You take the maximum of 30%. 30% is a benchmark. 30% of your train. Okay, remember your end train is 1744. Okay, take 30% of that or 100. Okay, so whichever is higher, use that as your initial window. Then you're going to test that on this one, class, the test which we call horizon. So this horizon can be based on the computation, it can be 200. Okay, so this will be our first slice. Okay, this will be our first fold. 400, 200. 400 will be your train, 200 will be your test. Okay, depends on the computation. And then, class, take note, this is data that's after 400, class. So there's no overlap there. Okay, next slice, class, will be put this together, class. Combine them, so you now have a larger training and then the next 200. So usually, this horizon class is constant. So pare-pareho yung horizon until such time that you reach that you're able to cover everything. All right. So that's now your initial window based on this computation. And then, as I said a while ago, this is now your horizon. Okay. So it's the number of your train 11744 minus whatever your initial window here is, and then divide by k minus 1. K stands for your folds. So it's 5 for k 5-fold or 10 if it's 10-fold. Okay, and then you're getting the floor again. Okay, and then here you have a condition. If the horizon is less than 1, if it turns out that the horizon is less than 1, you stop because the horizon cannot be a negative number. Okay. Okay. So here we run this class. I don't know if you have run this before, but run this now, and then you have this answer. So the number of our train, our training data is 1744. We know that. The initial window is 523. It's coming from this. So 30% of train compared with 100. So what prevails is 523. So what will happen now is that our initial window will be 523 observations. 523. And then our first test will be 305. Okay. So that will be your first slice. Okay. That will be your first, if it's a 5-fold cross-validation, that will be your first model class. We'll be able to generate a Ramsey here. Ramsey, root mean square error, based on the test data set. And then your next slide will now combine these two. So 523 plus 305, that will be 828. Okay. 828. This will now be your new training. And then your testing now will be the next 305. Okay. So it will just keep on moving by 305. And as I said, usually our horizon is the same. It's the same horizon. Okay. So let me just continue until such time na maubos na yung data natin. All right. In the next class, in the next ones here, so here we're creating slices. We are now asking R to generate the different slices. So we need the initial window, we defined it above. We need the horizon, it's above. Fixed window is equal to false means that your training data set will not be fixed. So it will keep on increasing as you add the previous test data set. Okay. And then here, okay, this is connected here, class. So you run those 3 code chunks, class. Can you do that? If you haven't run it, run this one, the slices, together with this one and this one, where we now create. Okay, this is now your train list K, where you're slicing, class, your train data set. And this is now your test list K, where you're slicing your test. Now the test here, class, is not the test for the final model. This is the test only for your in-house sample. Okay, the one that I mentioned to you that we're using just the train data set and then we're splitting it into train and test. Okay, so if you run that class, okay, just to make sure that there are no leaks. When you say no leak, there should be no data entering the training data set that is let's say more advanced, okay, than your testing data set. Your testing data set should always be more current than your training data set to avoid the look ahead bias. All right. So when you run that class, you have this. Okay. So take note how the slices are generated. You have 523, right? That's the first initial window, and then you have your test row 305. So your 305 remains the same, always 305, 305, 305 for 5 folds, class. So this is your cross validation class, a 5-fold cross validation. Notice now for the slice 2, it has now 828 training data set. Where did that come from? 523, the initial, plus 305. You add so that this now, the initial test will become part now of your train. Okay. And then you have now your next 305. Okay. Until the fifth fold class, 1439. Okay. So what does that mean? From data 1 up to data 1439 class. That will be your training. And then from 140 up to 2 to 180. That will be your 1744, I'm sorry. 1744. That will be 305 observations. That will be your last test row. Okay, so as I said, class, what will happen here? This is one model class. There will be an Ramsey here. Okay, Ramsey will be computed here, class. Also here, okay. So 5 Ramseys, it will be averaged. You also get the standard deviation of that. And then it will now create another model where you include all the training data set, the 1744 class. Okay, you now create this model that this will be your final class. So all in all, you have 5 Ramseys plus 1. Where is the 1 plus 1 coming from? From all your training data. Okay, so you have here changing train data and then changing test data. The numbers are the same for test data. Okay. All right. Pause for a while, class, and your confirmation, please, your feedback, if this is clear, class, this one. So very important, class, for cross-validation. And why is it done, class? Because you're able to, let's say this is random forest. Remember, for random forest, you can have 1,000 trees, class. The default is 1,000 trees. So this first model here, okay, this first fold has 1,000 trees. Then here you have another 1,000 trees, another 1,000 trees. Okay, so you're generating many models, class. You're coming up with many models, which and then you get the average of the Ramseys here, and then you the algorithm will call for the model, class, that best depicts our testing data set, our training data set, I mean, and then do it for the whole 1744. So that's your uh, sixth model. Okay. So pause for a while, class. Kindly chat, please. Are you able to follow along? Is it clear, class? Okay, thank you. Good. Good. Okay. And just to tell you, class, I'm really happy with this class in the sense that you're really very participative. Okay. Okay. I just appreciate the class. Okay. So next, let's move on, class. What happens now? What happens now, class? Okay. All right. So we will now generalize. Okay. This one. This is very important now. We will create now a custom, okay, train control. So what's this TC custom class? Train control from the carrot package. So we identify how will the resampling be done. There are other methods, class, but cross validation is one of the most popular one. Okay, so method cross validation. What will be our index? Remember this, class? Train list K. This is from the previous one. So this will be your training data set based on your index. So, asan yung class? Where is that? Yung progression niya, class, yung it keeps on increasing. And then this also, class, is your test data set. Take note, class, again, this is not your testing data set per se, the one where we generated from the original data. This is just test data set from your in sample data. In sample data is your training data, class. Okay. And then save predictions, final, which means, class, that, okay, it means that it will also run the model for all the training for the original training data set 1744. Because here, class, diba, you have a different sizes of train, okay, The test class, the test list is the same, 305. Okay, and then here class, return resampling all. It means it will save the Ramsey for fold number 1, Ramsey for fold number 2, Ramsey for fold number 3, which means you can access that, you can extract that. MAE, R squared. So everything is saved class, which we can extract. Okay. So now we're going to use this now. This is our TC custom class. And we're going to use this for all our algorithms. Okay. We're going to use this for random forest, for XGBoost, for SVM, etc. Okay. So first, let's now create a model, linear model class. So I'm creating this model, LM. I just call it time aware. I should have just called it LM model, but anyway, I already used this. So linear model, and then the function is train. Okay. And then take note class train. We're still using here the train data set. We're now modeling here using linear model, LM model. Okay. The dependent variable is target. This is our dependent variable associated with the dot here class indicates use all features. So we have 13 predictors, log1, log return, log1, log2, log3, SMA short, SMA long, RSI, MACD, etc. up to the exogenous Brent and VIX. Okay, what data are we going to model? The train data set, train data. Okay, so we're now going to make use of the training control, which cross validation, which we developed above, and okay, regress target. Okay, on all your predictors, training data set, method class is equal to LM. Okay, this is where later on we'll adjust this. For example, for decision tree, this will be our part. For SVM, this will be SVM. For ANN, this will be ANN, etc. So you have the same structure, but this time you're using a different model. TC control, training control, you're using TC custom. So the same for all. Ito yung class, di ba? Here. So whatever cross-validation we did above, that will also be followed for all the other models. So you have uniformity, and that makes now our comparison quite good because we know that we're actually using the same cross-validation. All right. And here also, this is very important class. I think I added some notes here, so maybe kindly just replace that. Okay. Control C. I'll just put this in the chat box. So what does this mean, class? Center and scale. Okay. First, center and scale class means that all the independent variables, all their values, we're going to subtract the mean. Okay, for example, RSI. So you have a value for RSI. Okay, let me just write that. Suppose the value for RSI, just an example, suppose it's 10. Okay, and the average of RSI, let's say, is, let's say, 3. If you get the average of RSI, it's 3. So you're going to subtract from each of the values of your RSI the mean, and also you're going to divide it by the standard deviation. Let's say the standard deviation is 1.1. Okay, so by subtracting the mean and the standard and dividing it by the standard deviation, this process is called centering and scaling. So what will happen, class, if you do this transformation? Number one, the mean of RSI, the average, okay, let's say RSI mean average will now be equal to 0. Okay, so it's centered. And then also the standard deviation, RSI, okay, let's say, let's call it sigma. Standard deviation of RSI will become 1. So that means it's scaled. In other words, because it's normalized. Okay. All right. So that's what we're doing here. Pre-process. Okay. So before we even process the linear model class, you already transform your variables. And what's the purpose, class? So that the comparison will be meaningful, class. Kasi same yung values ng RSI, etc. They're all centered and scaled. Okay. All right. So moving forward, class. Okay. Then summary. Okay. So if you run this class, if you run this linear model, this is the result. Yes. Okay. The formula is, your formula is, okay. The outcome, your target, regress on all data. Wait, let me run this again. Sorry. Okay. So these are the values of your, uh, these are your parameters, these are your predictors, and these are the significance. Okay, 3 stars means it's significant at 0.001, 3 stars. No? A dot here means it's not significant, but it may be significant at 10%. 1 star here means it's significant at here 5%, okay, which is the usual level of significance. Okay, however, class, if we take a look at the values here, the multiple R squared is 5.25%, quite low. And the adjusted R squared is 4.54. So, okay. All right. Now, I'd like us to look at the object that we created is LM time aware. Okay. If you take a look at that object, so for those of you who have finished, okay, how do I minimize this? It's getting in the way. Okay. Okay, dito lang muna. All right, so that's LM time aware. Let's take a look at this one, class. Okay, and you will see that it has many elements here. For those of you who have used LM before in either any subject of yours, Fin Arts, those of you who were my students before or even my students now, you notice that this output where we use trainControl contains many objects here, which are not found in any ordinary LM class. If you take a look at this class, you have here resample. Okay, if you click this class resample, here you have Ramsey class. So here you have 5 values of your Ramsey: 1, 2, 3, 4, 5. So these are the values of your Ramsey for split 1, split 2, up to split 5. Okay, because it's a 5-fold cross validation. If it was 10-fold, then there would be 5 values here. Also 5 values for R squared, 5 values for MAE, if there are intercepts, class. Okay, so these are your, if you remember, class, these are your training 0523 first 523 observations. This will be your first train, and then second train will be up to 828, if you recall, class, what we discussed a while ago, until the 5th train is up to, from data 1 up to 1439. Okay, so you have here many objects that are not found. Let's run first. Okay, let's run. I'm going to close this. Let's create, let's say, mod LM class, mod LM, and then let's let's regress target. This is your dependent variable class, right? Then shift associated with all of your features, and then data is equal to train underscore data. Okay, what are we doing here? We are also using LM class, okay, linear model. This is our dependent variable. This is our independent. These are our independent variables. So everything class, and it's where the data that we're going to regress on is our trained data. So let's run this class. Control Enter, and take a look, class, at mod LM. Mod LM here. It's also a list class. Let's print this. You can now see that this linear model, okay, contains less objects. Okay, for one class, we did not do cross-validation here, class. It's a pretty straightforward OLS process, class. Unlike this LM time aware, okay, we use cross-validation here. So we have more outputs from the caret package, class. I just want to point that out, class. All right, so let me just close this. Okay, let me just close the others, class. See, so many are open. Okay, here, go back. So where are we now? Okay, so we just finished this class. Okay, so just a note here, class. Okay, we did this right now, and we said that the adjusted R squared is quite low, 5.26%. Okay, and then we did this class. We viewed this object. What does it contain? Okay, and we can now inspect here. What are we doing here, class? We just print the resample results, class. Okay, so where can we get that? Print LM underscore timeware, and then, okay, so let me just show you. Our model is LM underscore timeware, right? Dollar, and you can see here the many different okay objects there. And then you can see here, class, resample here. Remember, resample contains the different values for, oops, here. So you can see here, Ramsey, R squared, MAE intercept, okay, for the different folds, different slices. Okay, this one, okay, and then we print cross-validation Ramsey and Ramsey mean, and also the standard deviation. So we're getting the mean, the average of, from your LM time aware, we get the resample and then get the object RMC. Remember, class, resample has RMC, has MAE, etc. And then just remove NA.RM if there's any NA there. And then we also get the standard deviation, also from that object Ramsey. Okay, here we just aggregate the results, LM timeware, and then dollar results. Okay, and then here also print the coefficients of LM timeware final model. Okay, let's see what the coefficients, class, will be the values of your parameters, the values of log of the log returns, RSI, etc., etc., etc. So when we print this, class, okay. So this one's, class, are ito yung ano, no, ito. Okay, print LM timeware results. Ito yun. The intercept, the Ramsey, the R squared, etc. Okay, these ones are sorry, results to, no? Results. Ito yun. Yung values ng mga predictors natin. There are 13, diba? 13 predictors. And then ito na, class, yung CV, yung values natin ng Ramsey, R squared, etc. dun sa in our cross validation. Okay, and then this last one will be, okay, this is the final model, class. Okay, Ramsey of 0.005, R squared, very low, class. Notice that yung final model, it even has a lower R squared compared to ito, class, diba? Ito yung R squared ng mababa din, class, ano, yung first fold. Mababa, it's 0.01%. And then here it became 1.5%. Third fold, it's 0.8%. Then this became 1.8%, and then this became 2%. Okay, so the average of this, okay, not the average, class, but rather the when we run the full train data set, it has an R squared of 1.26. So it can only explain 1.26% of the variability of your dependent variable target. So very low, not a good model, class. Okay, it cannot explain. Okay, now here, okay, this is just manually computing it. So I'll leave that to you, class. Ito time aware lang din naman yon. Tapos yung resample, then RMC. Okay, so we're just getting the mean. Okay, mean, standard deviation. Okay, I'll leave that to you, class. It's the same computation. Okay, now this is the final model, class. If we print the final model, okay, again, ano yung final model, class? This is the linear model on the complete trained data set, class, 1,744. So we perform a linear model on that. And you can see here, the final model, class, is how much is your 5.257? Okay, the final model. The R squared is 5.257. Still very low, class. Okay. All right. For this one, class, okay, this is just I'm creating here a function to compute for the Ramsey MAE R squared, and I added something here. Okay, this one I'm going to explain. You know already Ramsey, you know MAE mean absolute error R squared adjusted coefficient of determination, and then this one, class. Okay, okay. What's this, class? So this is your directional accuracy. Now sometimes we might not be as much interested as the the Ramsey, okay, or the let's say the accuracy of our predictions, okay, as compared to the directional accuracy. What's directional accuracy, class? Okay, so for example, you have on this day your returns went down, so it's negative, class, negative returns. So the question is, what is the prediction? Is the prediction also negative returns? So in this case, in that case, you have actual negative returns, and then the prediction is negative returns, then that's a match, that's good. If the prediction, if the actual is positive returns, and then the prediction is positive returns, class, then that's okay. What's not okay, class, if the returns, actual returns is negative, and then the prediction is +5, plus positive returns. So that's a wrong prediction, class, in terms of directional accuracy, class. So this one will now compute what percentage was correctly predicted in terms of the sign, class, in terms of the direction. Is it positive or negative? Sometimes in some instances, okay, so for example here, the direction accuracy could be equal to 0.5 or 50%. So in that case, class, there's no advantage of creating that model. It's just like flipping a coin. So parang, will the returns be positive? Will the returns go up tomorrow? Let's flip a coin, heads or tails, etc. So because the directional accuracy is only 50%, so it's just like flipping a coin. No? Parang kasi ang flipping a coin, class, 50% din yun eh, heads or tails. Okay, if the directional accuracy is greater than 50, let's say 55 or 60%, then that's good. So it means that our model is able to predict whether there will be a positive or negative returns better than any random choice. Okay, now this is very important metric, class, in trading. Okay, and then of course, lastly, when the directional accuracy is less than 0.5%, oh, all the more, class, that's worse than just coin flipping. Mag-coin flip na lang. So anyway, your model cannot predict correctly whether there will be increase or decrease in the returns. Okay. All right. So here, class, here, let's measure that. I'm creating this object metrics test. So it's a T-ball, class. The model is LM time aware. Okay. Here we have your Ramsey, root mean square error, and then that's OBS test, the actual and the predicted. So where's that coming from? This is coming from here, class. Our function, but function obs spread class. So square root of the mean of the observation minus the predicted squared. Okay, so these are your squared deviations, and then get the mean, and then get the square root. So that's where your Ramsey comes from. Errors squared. Ito yan. This is your error. The difference between your actual value and your predicted value, and then you square it. So that takes care class of your SE. Squared residuals, and then get the mean, ito yung M, no? And then get the root, R. That's why it's Ramsey class. So the formulas are here, class. Okay, so let's run this. Let's print the metrics. Okay, and you can see here what's the result, class. Let's take a look at this one, class. Oops, your directional accuracy is barely 50%, 50.7%. So walang masyadong value, class, yung model natin. Kasi it's not, pwede mag-flip coin na lang tayo, no, to determine if it's going to be a positive return or a negative return, yung directional returns, if it's positive or negative, or increase or decrease. Okay, and what's worse, class, is the R squared. It's negative 0.23. Okay, a negative R squared is always bad, class. Always bad. And I have here some explanation, which I just want you to read about. All right, and then here I'm plotting, class, the ggplot of your, this is your predicted value, and then your actual value. You can see that no good. No? The correlation is practically zero. Okay, you can't, it means that you cannot predict, class. It's so, walang relationship yung predicted at saka yung actual. Okay, that's why your R squared, class, is negative. All right, so this is just a summary, class, of what we did. Okay, and then here, quick summary lang of the process above. What did we do? We have our cross-validation phase. Think of this as model practicing on different chunks of your training data. You test your training data on the next unseen chunk. Okay, and then we get the average. And then we use all the training data to create the final model, class. And then we use it for predicting, class, yung test prediction natin. Okay, so okay, and then this is just a summary, class, of what we did yung slices. Sinamarize ko lang dito for you to try to recall. No? Andyan yung directional accuracy. Really, pareho lang to, class. It's the same as above. I just reproduce it here for you to check what's happening here. All right, so okay, so what do we have here now, class? Okay. All right, just run this, class, because here I'm introducing now. Okay, wow. Introducing 3 other packages. Okay. So where are we here? Okay, let me just backtrack a bit, no? Okay, I just wanted to point this out to you. Okay, here, class, here. All right. So when we run this, class, I'm not sure if we run this, class. Okay, but anyway, here, if we didn't run it, class, please run this, no? We are now using our model, class, on the new data, on the test data. Okay, I might have missed on this, class, but run this, class. Okay, new data, class, which means we're now using the model that we generated, the LM time aware, and run it on our test data, class. That's the main objective, class. We generate a model using, we first have cross validation, and then we have our final model where we use all the training data set, And once we have developed that final model, we run it class on our test data set. Okay, remember, that's what we mean by by overfitting. Okay, we don't use all the data. We set aside a test data set so that after we have generated the model using the trained data set, we now use that model on the test data set. Okay. So this class is our test data set, and we define the predicted test value, and then observed test value is just your actual value from your test data target. Okay. Yeah, I think we run this. Okay. So now the results of the model for our test test data set is from very far from ideal. The directional accuracy is just 50%. The R squared is negative. Okay. So that means that this LM is not a good candidate. It's not a good model class as far as your as far as our data is concerned. Because for our test data, you have a negative R squared, very bad. Okay. So let's now go to the other. Okay, I just want to point this out to you. Okay, so take note of this class, no? This is for our regression. When we create this now for the other algorithms, you change this name. But the notice here, class, you still have here the index. Okay, the final, return sample all. Okay, and then where's that? This is just a review class, sorry. Okay, now let's go here, class. Let's now go to our decision tree. Okay. Now take note, class, that we have now here the model for decision tree. We have the model for random forest. We have the model for support vector machines. We have the model for XGBoost, and we have the model for ANN. What's lacking now is just the comparison of all this. This is your XGBoost, which is quite long, class. I already provided you with the explanation. This is what you'll get for XGBoost, and then I provided some explanation for you to look at. And then this is your ANN. The last one is your ANN class, artificial neural network here. Okay. And then just comparing the models, class, which is the best model. So this is what I'm lacking, class, because of some bugs in my code. I'll just have to finalize that and provide you with the final. Konti na lang to, class, no? And then maybe I'll just give a short recording of this so that we're complete now with we have done machine learning regression. Okay, just let me just point this out, class. If you need to go as usual, class, just leave. But I'll just continue recording, class. So, okay. So where am I? Okay, here. So random forest, class. That's why I told you to do the research on the different algorithms. So take a look at this one, class. First, no, not random forest, but decision tree. So how does this differ now? The name of the model, we're not using LM, class, so I just changed the model, tree model. And then here, it's still the same train, same dependent and independent variables, same data class. The method is now changed. It's no longer LM, it's RPart now. The preprocess is still the same, center and scale. The train control is still the same class that which we defined using cross-validation above. And this time, I'm changing the tune length, okay? I made it 7 instead of just 5. And then the metric is the same. We just use Ramsey class. If you run this class, then you'll now have your random decision tree output. Okay, there you go. You can now see the Ramsey, the R squared, the MAE. The R squared class is lower than LM, 0.88, but at least it's positive. Okay, then you can get class you can get the final value class. Okay, this is the final value. And then you can get class the Ramsey R squared MAE for the final model. I just want to move on here, class, to random forest. Okay, I gave you a brief description of what random forest is, and then I just changed the name, RF model random forest. Same train function, target data method is equal to RF. So the convenient thing here is that you just change the method, RF na to, no? The pre-process is the same, center, scale. The train control is the same, TC custom, the one that we created. Dito lang nagbabago class sa tune length, sa entry. May mga specifics for your particular algorithm. So here, I just made also the tune length as 5, and then number of trees is 200. So if you run this class, this is now your random forest. Okay, it will now have its own results class. It will show the resampling values of Ramsey, MAE, etc. Okay, so while it's running class, the next one is support vector machines. This is hyperplane. It will create separations class among the data by this is quite difficult to visualize kasi hyperplane na to class eh. You're now creating n dimensions of planes. For us, a three-dimensional plane is still imaginable. But when you're now creating different planes class, that can be quite difficult to really visualize. So you still have 1744. This is for the random forest. And then you can see here R squared is, this is better than the decision tree as expected. No? This is a decision tree, not even not even 1%. No? Yung R squared. Okay? 0.88 lang. 0.88%. Ito, 2% something. But still, it's not a good figure class. But relatively, this is better than LM. This is better than decision tree. Okay? All right. Then we have SVM class. As I said, class, this is ang nabago dito yung SVM radial. Kasi maraming support vector machine type eh. So, isa sa pinaka-popular is the radial one. Okay, tune length, ginawa natin 7. And then if we print this class, you'll have this. Okay, again, 7 class. And then R squared is still just 1 point something percent. Okay, so they're not very far from each other. Okay, it looks like our parameters are not really good in order to predict our log returns, USD dollar. Okay, and then ito class, XGBoost. Now this will take quite long class. Kaya naglagay ako dito ng tick at saka ng talk. TikTok class in order. Install nyo muna yung package class na TikTok, TICTOC, so that it will time class. I will not run this now class kasi it took me around 3 minutes to generate the output. But the output will look like this class. Ito. Kinapi ko yung output, pinaste ko. Ito, ganyan yung lalabas, no? So you have values for your R squared, MAE, ganun din class, no? And in-explain ko dito class what this model does. Okay? So I leave you first to look at this, itong output ng XGBoost. And then lastly class yung ANN, artificial neural networks. Okay, maybe in what I'm going to send you will have a diagram of the ANN so you can see the neurons. Okay. Ito din class, similar to TikTok class, I gave a processing time, okay, start, kasi ito medyo matagal din, but not as long as yung XGBoost. And then end training time. And then I had printed yung training time ng ANN, which is end time minus start time. Okay, so you develop a model for this one class also. And then, okay, so that ends our discussion for today. And then, isa-summarize ko siya by, okay, take a look at this. Ito pwede natin i-run to class, no? We're going to evaluate and compare. So once you have run yung mga models natin class, then we can get the CV cross-validation results for each class. Okay? And then even, okay, sige. I hope you have, hindi siya pa mararana. Napapakita ko lang to class, no? Ito. Kasi, I have to run again yung mga previous one. Okay? Alright. So, anyway, skip mo ko muna to. I'll just include this in the recording of the last portion. Konti na lang naman yung class, no? So, okay. So,